slogan. It's a golf term. It's like maybe you get a do-over. It's kind of like, it was kind of like that. But hang in there, you know. If you're doing well, great, keep doing well. If you're having trouble, you know, again, there's me during office hours. There's the math department Tuesday, Thursday at 5, and I think it's in the math office where you can get help from students who are good at math. So, all right. We're going to start. I guess I want to pull the screen down. I decided somebody really wasn't thinking. It'd be really nice if this was off to the side. I could kind of write stuff here, stuff here. For anyone who's keeping track, we're going to start with section 5.3, which is about graphing and other things having to do with trig functions. I want to try and use the technology here to our advantage. And I encourage you to, you know, pull up Desmos and use your little calculator. I think Desmos is kind of better for this. We're going to start. We're going to look at one particular trig function, the sine function. But we're going to look at transformations of it and how they affect the graph. In particular, we're going to use some constants. And you can't really see the plus d over here. We're going to see what this does to the graph. Some of this is just the same as we saw with polynomial functions, transformations of polynomial functions. Okay, so let's start. Let's just take a look at this very simple graph. Oops. Can I say theta? Theta? I can. And it doesn't like that. All right. I guess you can say theta, but you can't use theta. So you've probably seen this picture on my board and elsewhere. This is a basic sine function. Do we have any physics or engineering majors here? Anybody? No. Well, this is ubiquitous in science. Even if you're a bio major, you're going to run into sine waves. Sine wave represents something in science we call a linear wave, which this may sound kind of contradictory. It's a wave where the wave doesn't affect the wave. That's not true of most real waves. Well, electronic waves it's true of. Water waves, not so much. Water gets in its own way. And more recently, you might have heard talk about gravity waves. We discovered gravity waves in the past few years. And they are not linear waves. The wave itself affects the wave. That's because, you need to know physics. But Einstein's theory says that gravity has to do with not just matter, but energy. And waves, gravity waves, have energy. So they not only, as they're moving along, not only are they affected by nothing, which is what gravity waves move through, but they're affected by themselves. So this is a sine wave. You kind of get the view of it. You should know it goes through 0, 0. And then again, period of 2 pi, it's a periodic function, it's going to go through 0 at 2 pi, and then every other 2 pi, negative 2 pi, 4 pi, 6 pi. It also goes through 0 here at pi, but that's, this is not the period, that's half the period. It doesn't repeat here, it repeats 2 pi. So let's just take a look at something simple. What happens if we take, just going to use x because Desmos likes it, plus some value, we'll add 1 to it. The screen's weird. Liking. Okay. All right. So you can see, like just like any other function, if you just add a fixed value, it moves it up. Since the sine wave goes between -1 and 1, if you add 1 to it, now you can see the bottom of the wave is the x-axis. So that's just a typical, should be an obvious transformation. The next thing we want to do is we want to see what happens if we multiply the function like this. The function. We're going to put some constant in front of it. So we'll just look at sine of 2x and see what that does. I think what I'm going to do is I'm going to just push this back, and we'll have a new function here. And that's the green line here. So what have we done? Well, at each point we've multiplied it by 2. We've widened it out. In the case of a periodic function like this distance, or half the distance between the least and the greatest value, so I should write that, f max plus f min 2. This is what we call the, I'm just going to abbreviate, amplitude of a wave. So you can see that constant in front of the function is just changing the amplitude. If I were to similarly half this, or then you get this blue line, which again the amplitude decreases. Okay. There's one other thing you can do with an amplitude. You could change the sign of this. What does that do? I guess just make that a second function too. You can see it's just reflecting the function across the x-axis. And so here you get kind of the negative at each point. So that's another thing you can do with that constant in front. The amplitude doesn't change because you're using a negative number. You don't get a negative amplitude. All right, so that's vertical translation and amplitude to stretch. All right, so the obvious next question is, if instead of multiplying by the function here, what if we were to change the value of the constant that we're multiplying x pi here when we call the function? This is the is actually the trickiest part, the hardest part to remember. Does anyone have any thoughts on what this is going to do? Yes?
Would it make the period of each wavelength smaller?
You got it right. The mistake people think is because it's a bigger number, sometimes it's going to make it greater. But let's see that. Let's see that. Exactly correct. See now my wave is going faster. If you think about specific values that you plug in, sine x versus 2 sine x, you can make this make sense. Or you can just remember that that's what it does. It's going to increase the period. Likewise, if I were to decrease this constant, now what have I done? I've stretched it out, I've doubled the period. So there seems to be an inverse relationship between that constant and the period. Now there is a value that actually goes along with that constant. It's called the frequency. And so what we have is this inverse relationship between the period and the frequency. Frequency is, well, the period is distance per cycle, or x values per cycle. So the frequency is cycles per x value. Now, you're most likely going to run into that in some kind of time where x is a time scale. So more common term, you're into cycles per second, which has another name, I guess we'll just throw out here. So this is why I don't want this thing in the center. There's no room. Cycles per second. This is the frequency. Cycles per second. Which also has the name hertz. As a physicist named Hertz. You call that hertz. 1 cycle per second, 1 hertz. So, right. Oh, I guess it's worth. I think it's worth developing. This is a relationship. It might be nice to actually know what that relationship is. So let's think about it. I have B here. So if B is 1, what's our period? Should be pretty straightforward. You just have like the sine of x. What's the period on that? I think everybody's here. Thankfully. What have we been talking about? Period of sine function. How long does it take to get from 0 back to 0? 2 pi. We said if b is 2, now it's pi, right? Or if b is a half, well, it doubles, it becomes 4 pi. So what's the relationship of b period here. Little thought experiment. Somehow related to 2 pi, right? When it's 1, it's 2 pi. When it's 2, it's pi. It's half, it's 4 pi. How do we get that? I emphasize this because you can, when we're done, you're going to memorize it, maybe, or write it down in your notes. It's always a nice thing to be able to figure these things out. It's not very hard. What am I doing with b to get these values? What am I doing with b to 2 pi? I'll rephrase this in language that is maybe closer to home. So, what I'm saying applies specifically to CS majors, but it applies to everybody, because everybody has to figure things out. If you're in a, unless you're an English major, this is, this is going to make sense. In computer science, what you spend your days doing is figuring out things like this. How do you get the computer to go from here to here? How do you get it to do this? Do I need to add something, subtract something? How do I combine these? Do I compare them? So you really have to be able to, focus your mind on minutia here. What do I do here to 2 pi to get these values given a certain b? Anyone? I'll just tell you, but it'd be better if you work it out. Yes. Oh, thank you. Pointing that out. Yes.
Well, I mean, making whatever b equals times the value equals a 2 pi. So,
1, 2, a half. What do I do with b to 2 pi to get this value?
well, you're multiplying it times a value to equal to 2 pi.
Oh, so, okay, good. b times, we'll call this, I don't know, let's call this p. b times p equals 2 pi. Is that what you're saying? Yeah. So what's p? No. There's an equation. P equals 2 pi. So P equals, what happened to B?
Over b.
Oops, that was great. That wasn't that hard. So the period is 2 pi divided by whatever this value is. I hope that was worth the angst we went through. Okay, so we looked at A, and we looked at D, and we looked at E. So now we want to look at C. What's C? Well, let's say we have sine of x minus some value. So this is going to be a translation in the x direction. All right, it's going to move the function this way. So let's just try something we already know what should be there. Yeah, I didn't say pi. Except I don't like that color. There, maybe if I write it again, maybe just cycle through them. Okay, so that's the blue. Well, it's not obvious. I mean, did we go this way or did we go that way? Maybe we should try pi over 4, just a little move. Okay, there we go. So we subtracted a value from x, and we just moved it over that amount. With any such trig function, if I say 2 pi, just what you think, you get the same function, because it's a periodic function. It repeats with period 2 pi. Okay, there's just one more detail I want to make it clear here. If you were looking at where did the chalk go? That's weird. Oh, here it is. If you looked at a function look like this, sine of say pi minus 2x. Yeah, there might be a plus d here, but we're going to ignore that. You want to be careful here. You might think, oh, let's do it the other way, so it's even less confusing. 2x minus pi. You might be inclined to think, well, I just have my 2x function, right, with shorter period, moved over pi. That would be a common error. But what would you say? 2 pi? It would be hard to see. Let's move it over 30 degrees. Well, we think 30 degrees. So let's take a look at that. 2x and 2x minus I over, I over 6. So we're thinking we just move that over 30 degrees, which is pi over 6 is about half. Oh, wait. This is a half, this is a quarter. Why is that not right? Because really what we have is sine 2 times x minus pi over 12. So now we can, in this form, we can read off this offset, which is pi over 12 or 15 degrees. So that's the one kind of error that students are inclined to make with this kind of question. All right, I just want to say a few more kind of practical things about all this, just for fun. Leave this up. Okay, there we go. So, anyone here from like a European country? No, okay. Maybe you're from a country where the voltage is different. In this country, our voltage that you find in the wall is 125 volts. That's actually, I think that is the amplitude. 125 down, 125. I'm not an electrical engineer, I'm not sure. It might be only we're going up 60 and down 60, I'm not sure. So between the top of the wave and the bottom, we have this voltage difference. It's repeating every 60 seconds. You get a hold of an oscilloscope, plug it into the wall, you're going to see exactly this. That's by intent. In European countries, and I'm sure you're all familiar with these are our plugs. The third plug is we call it ground wire, which is for safety. There's no voltage over it. In Europe, London, where I just was, they use 220 volts, 60 hertz. In Canada, they used to use, I think, 120, 50 hertz, but now I think they switched over. Any Canadians here? I think they're mostly switched over to 60 hertz. And they have these different kind of scary looking plugs here. There's one other kind of power you might run into. You might in your home, you might have a 220 volt circuit. They do that by combining two 110 volt circuits. And, typically that's to run either an electric range or a dryer. You need a lot of power. I live in an old 1910 San Francisco building, and they don't have that. We have to rewire it. So there's one more configuration you might run into. You could run into this in the US. And let me see if I can explain what this is. It's a special plug that has 4 connectors. One of them is kind of a ground, and the other 3 have signals on them. They all have 120 volt signals that are offset 1/3 the period. That's the phase, what we call a phase difference. And so you get something like this where, you get overlapping power, and you can get a lot more power out of it. You can get, you can get 240 volts kind of constant. And there are industrial machines that use this. I haven't come across one, but you can, if you work in some kind of factory, you might run into something like this. And if you want to build a factory, you call the electrical company and say, we need 240 3-phase system, and they go, sure, we know what that is. Okay, so that's most of what I want to say. I don't know, I think I'm just going to lean here for a second. Your standard sine wave, if you plug it into a speaker, you get a very pure tone. It's not going to be pure because as soon as you stick it into a speaker, there's a little distortion. And but you hear a high frequency single tone. If you were to add to it, say, something at a higher frequency, you're going to still have a periodic wave here. Let's move this out. But you're going to get a more nuanced tone. It's going to have 2 frequencies in it. And similarly, you could keep adding, let's say 0.2 sine 3x. You can keep adding frequencies, and you can take what was a pure tone, and if you're experienced in this, you could make it sound more like piano, trumpet, flute, because when you're playing these instruments, you're playing a particular note, that's the main frequency, but all these instruments sound different because these other overtones, as they're called, change the sound. Now, This isn't a music class, and I mention this for a particular reason. It really has nothing to do with music, which is if you have a periodic function like this, you can go the other way. You can break it down into its constituent frequencies. This is an advanced topic that physics majors and engineers are interested in. You won't run into it probably. It's called Fourier analysis. But it's kind of an interesting phenomenon that every tone can be broken up into pure tones this way. If you're building a radio, right, and you want to get a signal, you listen to the world, all these signals, but you create a little circuit so you filter out just the signal you want. And it's kind of an equivalent function here. So, all right, I just wanted to say it's just, you know, some of the stuff that pops out of trigonometry that you think this doesn't have anything to do with triangles or measurement, you know, that kind of measurement. So, all right. I think those of you keeping track of the book, we're gonna look a little further. I think it's 5. I think it's just more graphing or more functions. I guess I'm going to get rid of this. So we have the sine function, and what do we have here? We have the period. I have to move this down. Period is 2 pi. Max and min are 1 and minus 1. So the amplitude is just 1. Max minus min divided by 2. What's its domain? Domain of this function. What values can I plug into this function? No.
It can be x is less than or equal to 1 or x is minus 1 or greater than.
What's the range? All it's is 1 to minus 1. Okay, all right, that's the range. What's the domain? What values can I plug into it? Yes. I think I heard you right. It's all reals. Yeah, okay. All right, now let's move along pretty fast here. The cosine function. Okay. I don't draw that very well. Kind of looks like a sine function, right? It is. It's just a sine function moved over. Well, what's the offset? Well, you could think of it as we just moved it this way. What's that? Is that right? That's right. But you can also think of it as, well, we moved it, you know, how many fourths? Oh, wait, half. Half, that's a fourth. It's a fourth. We could just move it the other way. And any offset that you increase or decrease by 2 pi is going to work. So the period of cosine is therefore it's easy. Anybody? I have to say it's less than 2 pi. Just the same function moved over. So all the same values. Now we come upon tangent of x. We want to look into that a little. This tangent defined as the sine over the cosine. And the graph you should familiarize yourself with. Well, where is this not defined? Where is the cosine 0? 0 is defined, right? Where is it not defined? I guess maybe we want to go back to our unit circle. Where the cosine is the x and sine is the y coordinate. Where does the x coordinate become 0 as we're moving around? Where does the x coordinate, right, that's along the x-axis, where does it become 0? At what angle? Angles 90 degrees or pi over 2, right? So the domain, I'm not going to squeeze it in here with reals, but not equal to pi over 2, that's one of them. That's when I get down here, what angle have I gotten to? 270 or 3 pi over 2. And each of these plus or minus some multiple of 2 pi, right? So, okay. So 1, 2, 3, it's about pi over 2. What do you get when you divide by 0 on a polynomial? Well, it's the same thing with a trig function. You get an asymptote. We're also going to have one here. This is pi over 2, pi over 2, and somewhere around here, 3 pi over 2. Tangent function at 0 is 0, and it looks a little like a polynomial going up, but it becomes asymptotic. Same thing in the other direction, only going down. And then, since it's periodic, every 2 pi, is it every 2 pi? Wait a minute. Certainly, 2 pi is a period. But apparently, something happens when we combine the sine and cosine this way. And the period for the tangent is just pi. All right, so what's the maximum? know you know the next question. Go answer. What's the minimum?
Is that also for
Negative, yeah. So the amplitude doesn't really have an amplitude. Now, that doesn't mean you can't, like, say, what's 2 tan of x? And you might say, oh, it's got an amplitude of 1. But what that's going to do is it's just going to shape the graph a little differently. I guess it's going to, oh, actually, if I say 2, I got it backwards. It's going to increase slower. If I said half tangent of half x, it's going to increase quicker. Okay, you should be a little familiar with this and this table here. The other functions, well, we can talk about those too. The cotangent, just the sine, the cosine over the sine. Well, everything I kind of said to evaluate the tangent is true with a little change, right? It's going to have asymptotes at the at 0 and pi. It's going to go through pi over 2. And I guess maybe there's the tangent. Since it's the reciprocal, over here it's going to have positive values. It's going to look like this. And to the right, it's going to have negative values. And just like the tangent function, it's of course going to be periodic. Not the best drawing, but all right, that's the cotangent. So cosine over the sine. It's going to also have a period of pi. Same. Domain, well, the domain is going to be r, but x not equal to 0 and I, and again, each of these multiply by, you can add multiples of 2i. This is no way to draw that. All right, so you should be familiar with, at the very least, this part of the table. The other functions, they're somewhat, I wouldn't say they're useless, but they don't come up as much. You might be doing some kind of homework problem where instead of needing the cosine, multiplying something by the cosine, you're dividing by the cosine. So you really want the secant function, but your calculator doesn't have it. So you just have to use 1 over the cosine anyway. However, my way of dealing with the graphs of these is don't try and just graph a secant or a cosecant function. Graph the reciprocal first. So let's say we want to look at the cosecant. So I'm going to get cosecant of x. This is going to translate into 2 pi. The max is going to be infinity, minus infinity. So there's no amplitude still. And we'll talk about the range and domain in a second. But again, you just graph a sine function. That's a sine function. What does 1 over the sine function look like? Well, the sine function has zeros at 0 and pi and 2 pi. So again, these are going to be asymptotes. And the function we want to draw is just the reciprocal. So at 1, it's going to intersect, and then it's going to go off into infinity, negative infinity. And of course, it's going to be periodic. So that's the cosecant function. Find the secant, you just graph the cosine function. And you would get the same, better. Okay. All right, let's see if there's anything else. Domain, well, it's going to be real numbers not equal to, what am I doing? The cosecant, 0 and pi and 2 pi n plus each of these. The range for both these functions, the cosecant and the secant, is going to be what? It's going to be 1 to infinity, but also negative infinity and negative 1. So the cosecant is eliminated from this part of the graph. All right, so you should be familiar with all these functions. There are domains and ranges, there are periods, which again, you can see it's pretty simple. It's either sine, cosine, cosecant, secant, in which case it's 2 pi. Tangent and cotangent is pi. Modified by that b value, right? You divide by b and you get the period. If it's 1, you get these values. Just a little more to say. Why don't we take a break for 5 minutes? Check your email, so forth. Good. All right. I'm gonna work on the easy one first. So we've got log to the base 4 of x plus 12, log to the base 4 of 3 equals log to the base 4 of 5 plus log to the base 4 of 2x minus 3. So what we want to do is we want to use our laws of logs, which tell us the log to the base 4 of x plus 12 plus the log to the base 4 of... Oh, you got another one. Well, I don't want you to miss this because it's your question. Okay. So this is going to be the log to the base 4 of 3 times x plus 12. Similarly, over here we use our laws of logs. This is log to the base 4 of 5 times 2x minus 3. And now, using the fact that the log function is 1 to 1, well, that's one argument. The other would be to raise each of these to 4. And we just end up with a nice little algebra problem. 3x plus 12 equals 5 times 2x minus 3. Now, I will do that. Do you wish me to do that? A lot of feedback in this class. I should make 50% of my grade fast participation, that would really change things, right? All right. 3x plus 36 equals 10x minus 2. So 7x equals 51. Our brain has stopped functioning. You divide 51 by 7. Did I do all my additions properly? 40, 51, 7, yeah, okay. That's how you do a problem like number 54. You use logs or exponential rules to make it an algebra problem. This one looks a little harder. I'm scratching my head though. I'm thinking, you got a base of 2 and a base of 3. You can't just, well, you could just say log to the base 2 of the whole thing and go from there. But that probably would do it. So then you'd have 3x plus, well, there's still an x there. It's kind of ugly. What I think you should do for something like this is probably 3x plus 1 equals 3x minus 2. You might want to see if you can kind of skin this cat this way. Let's raise these both to the 6th power. That's 2 times 3. So here, this becomes 2 to the 3 times 2, 3x plus 1. Nah, that's not going to work. I don't know, what was I thinking? No, that's not going to work. Okay, well, that's what you do. You try something, if it doesn't work, try something else. All right. 2 to the 3x plus 1 equals 3 to the x minus 2. Well, next thing to try is let's find the log to the base 2 of both sides. Right? Log to the base 2. Log to the base 2. So here, that's going to go away. We're going to get 3x plus 1, which is nice. And here we're going to get log to the base 2 of 3 to the x minus 2, which is not nice. Is it? Ah, I missed the obvious. This is x minus 2 and log to the base 2 of 3. Well, this is just a number. So now I just have a little algebraic expression again. Right? All right. 3x minus log to the base. Let's just give this a name for the moment. We'll call it A. 3 minus ax equals 1 minus 2a. So this is 3 x minus a equals 1 minus 2a. So 3 equals 1. That's what I want to do. X minus a equals 1 minus 2a over 3. Or x equals a plus 1 minus 2a over 3. And now I just have to, kind of place a here with log to the base 2 of 3. So find x in decimal and log form. So I guess this is kind of log form, and then if you use your calculator, you find the decimal. Yes?
How do you get 3 out of 3x minus 8x?
Oh, I make a mistake. That's how, and nobody watches except you. That's how. Thank you. X times 3 minus A equals 1 minus 2A. Okay, there, it's much easier. So X is just immediately X equals 1 minus 2A over 3 minus A. And then you plug in. All right. Okay, find the inverse of, no, can I erase everything now except the last problem? Yeah, the whole, I mean, this is the problem with math, especially at this high rate of speed. Everything builds, right? You didn't really get those laws for logs and exponents. Now we add some algebra. You know, if you're keeping up, it's fine, but if not, you kind of can get lost in this. All right. Find the inverse of log to the base 2 equals log to the base 2 of x minus 1. In the world of mathematics, when you do a problem like this and you're finding the inverse, you want to be a little careful about what the domain and ranges are. We're going to skip that because we're basically going to do the algebra part of this. But you might want to note that if x is less than 1, wait a minute. Yeah, if x is less than 1, this is not defined, it's not in the domain. So that tells us something about the range of the inverse. So, again, my process of finding inverses is, first we're going to write it this way, y equals log to the base 2 of x minus 1. We're going to switch x and y, which is kind of what doing the inverse is. And now we just want to solve for y. Well, remember, log to the base b x equals, I don't know what to call it, a. B is the base. A, the log, is an exponent. The inverses. So we can do the same thing here. 2 is the base, x is the exponent, and that's 1 minus 1. So we get y equals 2x, 2 to the x, minus 1. And if you like, we write inverse of x equals 2 to the x minus 1. Now, I don't think I did that right, did I? No, I didn't. Now, if you want to think of it as this function and this function kind of undo each other, then you can kind of think it through. I have some value, I subtract 1, and I find its log. That's how I find the range, something in the range. I take that number, I now raise it 2 to that value and add the 1 back. That's how I undo subtracting the 1. That's what an inverse does. So, but again, you know, you can be very mechanical about it. As long as you, I mean, once you get to this part, that's where the work starts. You have to use your laws of logs, you know, or you can do this. You can do this a couple ways too. I mean, you could have an intermediate step where you say, well, let's raise everything to 2. So let's raise 2 to everything. 2 to the x equals log to the base 2 1 x1, and then recognizing 2 to the x and log to the base 2 are inverses, so this just becomes y minus 1. That's one way to handle it, or think about it. All right, we good on homework problems? Everybody? I think we're not quite done with 5.5, but we're almost done. There's an important feature of the tangent function that you should be aware of. If I have some linear equation, some simple a line, right? That is a function, we call it 2x. So you should all know how to draw this line. The y-intercept is 0, so it goes through 0. And change in y of the y over delta x is our slope, which in this case just happens to be 2. Now, we look at the angle here, theta, and we draw a triangle here. We have the adjacent side, the opposite side, and the hypotenuse. And by definition, the tangent of theta is the sine over the cosine, so it's the opposite over the adjacent. But this is just a delta x, and this is just a delta y. Which means that you have a line, you know its slope, you also know the tangent of the angle it makes with respect to the x-axis here. And not too bad if you can be. Well, if I told you you have some line and it goes through some point, let's make something up 5. And the angle it makes is, say, 30 degrees. And I say, what's the equation of that line? Well, it's, of course, y equals mx plus b. Well, b I know is 5. So what's m? Well, m is the tangent of this angle. X plus 5. So now our only job is to figure out what tangent of 30 degrees is. Well, if you have a 30-degree angle, I hope at this point you know that the shorter side is a half, the hypotenuse is 1, and the longer side is square root of 3 over 2. So the opposite over the adjacent is 1/2 over square root of 3 over 2, or 1 over the square root of 3. So that makes our equation just y equals 1 over the square root of 3x. That's our slope plus our intercept. So that's one thing you could do with this. Another is if you're given some equation. And someone says, well, what angle is that at? Well, you know the tangent of the angle is 3. Oh, what good is that? Assuming this is a practical problem, we'll learn in a coming material that we could just call this the inverse tangent of 3. We're careful. Or we can use our calculator and say, all right, second tangent inverse 3, 1.2490 something, right? So we can get the slope in that manner. So that's why this is a valuable piece of information. Tangent of the angle that a line makes with respect to the x-axis is its slope. All right. I guess we're gonna get started on inverse trig function. But there's this thing I like to show people. It's really not part of the class. It's just so much. To me, it's just when I learn this kind of stuff. This is so much fun to know because nobody knows this almost, and now you will. So, I don't know when the first time I saw this picture I'm about to show you. It's probably like 4th grade or something. But you're all going to recognize this. As soon as I find the right place. Right here. Oh, where's my picture? Oh, poetry patience. Oh, not even in the right ballpark. All right. How many of you have not ever seen this map of the world? Anybody not see these? Everybody recognizes this? Put this up in grammar schools all over the world. What the heck is this? This is a funny looking picture. Notice Greenland and South America are about the same size. I don't know how many of you studied geography in any detail. Greenland is not the size of South America, right? There's something funny about this picture. Okay? Anyone run into this? It's called a Mercator projection. You might say to yourself, why do we have this picture up everywhere? It's so distorted. And while we're at it, where's the North Pole? Do you know where the North Pole would be on this picture? Or the South Pole? It's up there at infinity. You extend this map, it gets elongated to the point where the North Pole and the South Pole are infinitely far down. That's weird. Well, this your whole life, and never really thought, what the heck is going on? I mean, you might want to Google Mercator now, because we have internet. So, okay. So the first piece of knowledge here is if I'm graphing this, and I want to know, I want to take my my latitude, right? 0 degrees at the equator, moves up, it's going to be 90 degrees at the poles. How do I know how far, how do I know what my y is going to be for some latitude on this graph? And the answer is, it's the tangent of theta. Okay? So that's the first question. What is it? Well, so if you think about it, the tangent of 90 degrees is infinity. Just like I said, the North Pole's up at infinity. South Pole's down at negative infinity. The real question is, why? Anybody have any inkling? Why would we make this weirdly distorted picture of the world? Because I mean, you see the problem, you've got a globe, it's a sphere, and you want to squash it down on a piece of paper. There's lots of ways to do it. There are lots of different projections. Okay, so the big secret is that probably in the 1700s and 1800s, commerce was about, and maybe world domination. Think about Spain and England. It was about sailing the seas. And if you're a sailor, you wanted a map so you could get from one place to another. If you have a map of a sphere, well, you might have a globe on your boat. But how do you figure out on your map to get from one place to another? Because you know a straight line on a map is not necessarily a straight line. Well, the answer is this Mercator projection has the magic property that straight lines on the Mercator projection are straight lines on the Earth, or what we call a great circle. So all of a sudden, tangent function, it's kind of magical in that way. Now, I don't think we have any sailors here, so, and we have GPS anyway, right? So we just want to go there and tell us. But this is historically where this map comes from. It was the map that sailors would use, and it ended up in your grammar school walls. So that's kind of fascinating. All right, enough history lesson. Hope you like that. All right. So now, we kind of have a big job here to tackle. The book seems to cover this in 2 places, and I'm not really sure where I'm getting this from, but it's either section 5.5, which has to do with triangles, 6.4, which is the section on using the big circle. But we want to look at this idea of inverse trig functions. It might seem as simple as using your calculator and using that second key and finding values. But as it turns out, it's a lot trickier than that. You have to be very careful. You recall, when we were first looking at inverse functions, we might have a function like x squared. And the act of finding inverse has the effect of reflecting that function across y equals x. But if I were to reflect the entire function, I would get the graph of a relation that would fail the vertical line test. So when we create inverses, we sometimes have to adjust or truncate the domain, which we do in this case. We just say, all right, domain is x greater than or equal to 0. So now our inverse is the square root of x. We have the same problem, only to a greater degree with trig functions. If I take the sine function, now I try and reflect it across y equals x. And here I get two values out of the relation. Here, because it's periodic, I'm going to get an infinite number. So I have to be a little more careful. So how do I do this? How do I adjust this function? Well, we do it individually for each function. We have to look at it. In the case of the sine function, we're going to truncate the domain between negative pi over 2 and pi over 2. So instead of this very complicated yeast here, we're just going to get a function that kind of looks like this. Now, that's completely arbitrary. You could use another piece, and it would be up here, or a piece down here. We just need to make this 1-to-1. But it's important to know this particular domain because, as you will find, that's what your calculator uses. All right? Okay, so let's think about this. The sine function, sine of x, domain, well, it was all real numbers, but now we're just going to use negative pi over 2, pi over 2. And what's its range? What's the range of the sine function? Yeah, it's just negative 1-to-1. So the inverse function is just going to swap these two. If you try with your calculator to plug in a number outside of negative 1 and 1, you're going to get, what does it say? I think it says, just want to be accurate here. I think I know what it says. I think it says domain error. But why don't I just say inverse sine of 2. Error, domain. In addition, if you put a number in between these two, you're going to get one of these numbers back, between negative pi over 2 or pi over 10. Which means that if the answer you're really looking for is out here, you're going to have to do some adjustment to find that number. All right, so that's the sine. Another way of looking at it, if you want to look at the circular functions, the circular definition, is that we use the same definition, which is cosine, sine is the coordinates of the circle, the unit circle. For the inverse function, what we do is we limit the domain of our function to just this side of the circle. That way, when we find the inverse, right, it still passes the vertical line test, or if you like, it's going to pass the horizontal line test here. It would be nice, wishful thinking, if the same rules applied to the cosine. But of course they don't. With the cosine, we're now going to have to use the same color. We're going to use this part of the circle. The domain we're going to pick is 0 to pi, and of course it has the same range. So the range of the inverse cosine, domain of the inverse cosine, of course, is -1 to 1, but the range is going to be from 0 to pi. Now, there are plenty of angles whose outside of this that you're not going to get from the inverse function. So sometimes, when you're doing a problem, you have to kind of look at other features here. What does the inverse cosine look like? It's all, the range is all positive, and it's, again, one of these sine wave, cosine waves on its side, and it looks like this. I want to clarify a bit of terminology here. We can write sine inverse of x. There's an equivalent, you can say arc sine of x. However, you may, I don't know if we'll run into this, but you may run into this somewhere in math, where we write a function this way. Well, actually, we write something this way. Capital A, arc sine of x. What do we mean by that? This is a function. When we add a capital A, we're relaxing that requirement. It's no longer a function, it's a relation, which means it can be one to many. This relation is, like, let's say I was to say, what's the arc with capital? Well, this is the cosine of x of, say, 1/2. So So you can see this is going to pass through an infinite number of points. And that's what this refers to, the relation that says we're going from a half to all those points, which we could write. Well, we'd have to be a little careful, but we can start off by saying, well, sure, 2 pi n. Obviously, every 2 pi n. That actually doesn't capture them all, and we'll do a problem to show that. All right. All right, there's one more question. No. There's one more function we want to take a close look at. Inverse function. I don't have room on my table here. I'll just extend the table. That's the well, let's look at the tangent. And the inverse tangent. So the domain of the tangent, and now I guess you should all know it's real numbers, where x is not equal to pi n. So that's where the cosine is 0, and that's where it's undefined. Range is all real numbers. So that immediately tells me that the inverse tangent function is going to have a domain of all real numbers, and its range is going to include, now this kind of gets fun. We need a picture here. The inverse tangent function kind of looks like this. It's what you get if you took one piece of the tangent function and kind of flipped it over. So its range is actually what? Negative pi over 2 to pi over 2. To be clear, that's an open. You'll never get to these, negative pi over 2 and pi over 2. I think that's the basics for inverse function. Let's do we'll do a few problems to get a feel for this difficulty I mentioned, where the calculator might give you a solution, but that's not adequate. All right, any questions about this so far? This is probably one of the thorniest pieces of parts of this class. So let's see practical application. Okay. Find all angles whose sine is 1 over the square root of 2. Okay. Well, we know sine of 1 over, sine of pi over 4 is 1 over the square root of 2. It's a kind of raw picture. Pi over 4 is 45 degrees. So clearly, sine of pi over 4 is 1 over the square root of 2. So inverse sine of 1 over the square root of 2 is, of course, pi over 4. But being periodic, if 45 over pi over 4 has this sign, you go all the way around, add another 2 pi, or subtract it, and we can do that as many times as we want. So that turns out to be half the answer. Recall that the sine is the y value of this coordinate. Well, if you draw a horizontal line, you can see that this point over here is going to have the same sign. Well, what is this? This is 45 plus 90 is 135. So the sine of 1 plus square root of 2 is also 2 pi over 4 plus 2 pi. And that's the answer. There's an infinite number of them. Every one of these values, finding the sine, will give you 1 over the square root of 2. And I write that this way, pi over 4 plus 2 pi n, comma, 2 pi over 4 plus 2 pi n